experiencing very strong shaking. Wow. I think we need to get under the desk.
Now to a string of recent earthquakes here in Southern California.
There hasn't been a big earthquake on the southern San Andreas Fault for a long time.
Recent earthquakes in the Sierra remind us of California's other active earthquake zones, especially the ones on the San Andreas Fault. NASA recently revealed a critical crack in this fault. Some conspiracy theories about the San Andreas Fault exist, but this info is for entertainment only. Scientists warn that a strong earthquake could hit areas near the San Andreas Fault soon. The southern part of the fault hasn't had a big quake in a long time, but the residents of that area need to be prepared for the worst. Understanding of the San Andreas Fault. The San Andreas Fault is a major geological feature in California. It stretches about 1,200 kilometers through the state. It is a continental right lateral strike-slip transform fault. The Pacific Plate and the North American Plate slide by each other. Scientists have divided the fault into three main segments: northern, central, and southern. Each segment has distinct characteristics and varying levels of earthquake risk. The fault's movement or slip rate averages between 20 and 35 millimeters per year. In Northern California, the San Andreas Fault ends offshore near Eureka at the Mendocino Triple Junction. This junction is a meeting point for three tectonic plates. Here, the Cascadia subduction zone intersects with the fault. Some scientists suggest that a big quake along the Cascadia subduction zone could trigger a rupture along the San Andreas Fault. In Southern California, the fault terminates near Bombay Beach in the Salton Sea. In this area, the plate motion shifts from right lateral to divergent, causing the land to pull apart. This region, known as the Salton Trough, is gradually forming a new mid-ocean ridge, an extension of the Gulf of California. The Colorado River has deposited sediment in this trough, preventing it from filling with seawater from the Gulf. In 1985, Professor Andrew Lawson of UC Berkeley identified the San Andreas Fault. After the 1906 San Francisco earthquake, Lawson was asked to find its cause. He mapped the locations of surface ruptures where roads, fences, and other features had shifted. His findings showed that these offsets aligned perfectly along the fault he had discovered. He concluded that the fault caused the earthquake. This fault line ran through San Andreas Lake, a sag pond created by an extensional step over in the fault. This natural depression collected water, forming the lake. Contrary to popular belief, Lawson did not name the fault after the lake. His reports from 1895 and 1908 show that he named it after the nearby San Andreas Valley. Lawson also determined that the fault extended into Southern California. In 1953, geologist Thomas Dibley concluded that the fault could move laterally for hundreds of miles. From 2004 to 2007, a National Science Foundation project called the San Andreas Fault Observatory at Depth, SAFOD, drilled into the fault near Parkfield, California. The goal was to collect core samples. Then we would study them with geophysical and geochemical methods. This would help us better understand the fault's behavior below the surface. 1906, San Andreas Fault earthquake. The San Andreas Fault is a transform fault. It marks the boundary between the Pacific and North American plates. This strike-slip fault has lateral movement. The Pacific Plate is moving north relative to the North American Plate. It runs along California from the Salton Sea to Cape Mendocino. It is about 810 miles long. The fault has a maximum surface displacement of about 20 feet. Geodetic measurements show displacements of up to 28 feet. The 1906 earthquake occurred before the development of the Richter magnitude scale. Modern estimates place its magnitude at 7.9 on the moment magnitude scale. Estimates range from 7.7 to 8.3. A Journal of Geophysical Research study shows major crustal changes before and after the quake. The earthquake released strain along the fault. It damaged a 280-mile segment of the San Andreas Fault. The rupture extended both north and south for a total of 296 miles. The shaking was felt from Oregon to Los Angeles and as far inland as central Nevada. The main shock was preceded by a strong foreshock occurring a short time before. The main earthquake's shaking lasted around 42 seconds. Before the 1906 quake, Northern California had more minor quakes than ever before in recorded history. Once thought to be precursors to the 1906 event, these tremors are now linked to seasonal sediment loads in coastal bays from gold rush hydraulic mining. For many years, the epicenter of the quake was believed to be near Olema in Marin County. In the 1906, a seismologist from UC Berkeley proposed it was more likely offshore, northwest of San Francisco, from the Golden Gate. Recent analyses support this offshore location, though some uncertainty remains. A local tsunami recorded at the San Francisco Presidio supports this. It had a wave amplitude of about 3 inches and a period of 40 to 45 minutes. Triangulation data before and after the quake suggests the rupture was about 310 miles long. This matches the intensity data. Seismological data show shorter rupture lengths. We can explain this by considering supershear propagation. It is now recognized in many strike-slip fault earthquakes. In 2019, researchers confirmed earlier estimates. They found the hypocenter offshore of San Francisco, or near San Juan Bautista. Andrew Lawson's 1908 report found that shaking intensity linked to geologic conditions. Sediment-filled valleys shook more than bedrock locations. The worst shaking was in former bays, where soil liquefaction had occurred. The modified Mercalli scale rated the shaking as 11, extreme, in San Francisco and Santa Rosa. Following the main shock, there were numerous aftershocks and remotely triggered events. Aftershocks proved scarce, clustering distant from the 1906 rupture zone. The largest aftershock was west of Eureka. It had a size of about 6.5 magnitudes. A similar-sized quake hit near Cape Mendocino over 3 years later. Events triggered from a distance included a swarm in the Imperial Valley. It culminated in a quake of about 6.1 magnitude. Another event had an estimated magnitude of 5.0 under Santa Monica Bay. The 1989 San Francisco-Oakland earthquake. The Loma Prieta quake, or the San Francisco-Oakland earthquake, hit the Bay Area in California on October 17, 1989. The quake hit just before 5 p.m. local time, moments before the start of the third game of the World Series at Candlestick Park in San Francisco. With a moment magnitude of 6.9, this earthquake was the most powerful to hit the region since the infamous San Francisco earthquake of 1906. The quake's epicenter was in the forest of Nisene Marks State Park, near Loma Prieta Peak in the Santa Cruz Mountains. It is about 60 miles south of San Francisco. The earthquake lasted around 15 seconds, but in that brief time, it caused extensive damage throughout the region. San Francisco and Oakland saw the worst destruction. Other communities like Alameda, Santa Clara, Santa Cruz, and Monterey were also hit hard. 63 people died, and 3,800 suffered injuries. Property damage was widespread, with losses estimated at around $6 billion. The earthquake had a devastating consequence. The Cypress Street Viaduct, part of the Nimitz Freeway in Oakland, collapsed. This collapse resulted in the majority of the earthquake-related fatalities. Additionally, a section of the upper deck of the San Francisco-Oakland Bay Bridge gave way, further illustrating the severity of the event. The damage to the Bay Area's transport system showed its bridges and roads were vulnerable. This prompted a seismic retrofitting of all the area's bridges in the years that followed. In San Francisco, the Marina District was hit hard. Its foundation on filled land, made of loose, sandy soil, caused this. This type of ground exacerbated the quake's impact, leading to significant damage to buildings in the district. Likewise, in Santa Cruz, many old unreinforced masonry buildings, some 50 to 100 years old, failed completely. The timing of the earthquake was remarkable. It struck just as the third game of the 1989 World Series was about to begin. It was between the San Francisco Giants and the Oakland Athletics. The event was broadcast live on TV. Millions of viewers saw the quake's aftermath. Aerial footage from the Goodyear blimp offered a bird's-eye view of the devastation. It brought the disaster into homes across the country. The damage in both cities was extensive. So, the World Series was suspended for 10 days. The event became known as the Earthquake Series. This earthquake spurred major advances in seismology and preparedness. It led to the development of early warning systems. The event showed the need to prepare for natural disasters. It also highlighted the role of seismology labs like Berkeley's in reducing earthquake risks. Recent findings and predictions. In 2006, Yuri Fialko, an associate professor, published a study in Nature. He is at the Scripps Institution of Oceanography's Green Institute of Geophysics and Planetary Physics. This study found that the San Andreas Fault is stressed enough to trigger a quake above magnitude 7.0 on the moment magnitude scale. The study also indicated that the risk of a large earthquake might be rising faster than scientists had thought. The current risk is mainly focused on the southern section of the fault, particularly around Los Angeles. This is because in 1857 and 1906, significant earthquakes occurred on the central and northern segments of the fault. However, the southern section has not experienced a similar rupture for at least 300 years. The study says a major earthquake in the southern San Andreas Fault would likely cause severe damage to the Palm Springs, Indio area. It would also hit cities in San Bernardino, Riverside, and Imperial counties in California, and in Mexicali Municipality in Baja California. The impact would be severe. It could cause major damage across much of Southern California, including Los Angeles, Ventura, Orange, and San Diego counties. It would also affect Ensenada and Tijuana in Baja California, San Luis Rio Colorado in Sonora, and Yuma, Arizona. Older buildings on loose gravel or in coastal areas are at risk of soil liquefaction. They would be especially vulnerable. Fialko noted, all these data suggest the fault is ready for a big earthquake. But we cannot tell when it will trigger and when the quake will occur. It could be tomorrow, or it could be 10 years or more from now. Since the study's publication, there has not been a significant earthquake in the Los Angeles area. In the 18 years since the USGS has released 2 major reports, they have differing predictions about the risk of future earthquakes. Accurate prediction of major earthquakes that would warrant heightened precautions remains challenging. The USGS's latest forecast, called UCERF3, came out in November 2013. It is estimated that a magnitude 6.7 or greater earthquake occurs about once every 6.7 years statewide. The same report estimated a 7% chance of an 8.0 or greater earthquake along the San Andreas Fault in the next 30 years. A different USGS study in 2008 assessed the potential impacts of a major earthquake in Southern California. It predicted a magnitude 8.8 quake along the southern San Andreas Fault could cause about 1,800 deaths and $213 billion in damage. A 2008 paper studied past earthquakes along the Pacific coast. It found a timing link between seismic events on the northern San Andreas Fault and the southern Cascadia subduction zone, which runs from Vancouver Island to northern California. Scientists believe that quakes on the Cascadia subduction zone may have triggered many major quakes on the northern San Andreas Fault in the last 3,000 years. Correlated events display ruptures originating in the north and progressing southward. However, the 1906 San Francisco earthquake seems an exception. It was preceded by plate movement from south to north and did not follow a major quake in the Cascadia zone. Monitoring earthquake risks. INSAR is a key technology. It monitors changes in the Earth's surface. INSAR uses radar images taken at different times. It allows scientists to measure ground displacement with high precision. It helps track shifts in the Earth's surface over time. This gives insights into fault movements. Another essential tool in this monitoring process is ground-based GPS stations. Stations situated on fault lines check their precise positions constantly. Even minor shifts in these positions can signal movement along the fault. This real-time data is crucial for understanding and predicting fault activity. Seismographs are also integral to earthquake monitoring. These instruments record vibrations in the Earth's crust. Spread across various regions, they can detect even the smallest seismic waves. Analyzing seismograph data helps scientists determine the location, depth, and magnitude of earthquakes. This information is vital. It helps us understand fault behavior. It also helps us spot patterns that might signal a big quake is coming. NASA uses aerial and ground surveys, along with satellite and ground-based tech, to improve fault monitoring. Drones and planes with cameras and sensors measure fault lines. They capture detailed images too. Ground teams use laser scanning technology, known as LiDAR, to create detailed terrain maps. These surveys offer a closer look at the fault and can reveal changes not visible from space. Recent NASA studies have found important things about the San Andreas Fault. They focus on a specific crack within it. This crack is located in a sensitive area of the fault known for producing major earthquakes in the past. Over time, the crack has grown larger, indicating increasing stress and pressure within the fault. NASA's data shows the crack runs deep into the Earth's crust. This is a sign of a potentially powerful seismic event. Observations reveal that the crack is not only widening, but also experiencing increased movement. This means that the two sides of the fault are sliding past each other more frequently. This activity suggests the fault may be close to an earthquake. It could release a lot of energy. NASA's research found a troubling rate of stress buildup along this part of the fault. Data indicates that stress is building up more rapidly than previously observed. This rapid buildup of stress warns that the fault may soon trigger a major earthquake. San Andreas Fault's mysterious signals. New research suggests that a section of the San Andreas Fault, where earthquakes occur often, might emit a signal before an earthquake. This signal could indicate the opening and closing of cracks beneath the Earth's surface. This section, called Parkfield in Central California, has an earthquake every 22 years. The last quake occurred in 2004, so another one might be approaching. A study published on March 22 in Frontiers in Earth Science found that the signal has not been detected in the fault segment recently. Also, this section did not behave the same as before the 2004 earthquake. These differences might mean the next earthquake is not imminent, or they might indicate a different epicenter than in 2004, just southeast of Parkfield. Luca Malagnini is the study's lead author. He directs research at Italy's National Institute of Geophysics and Volcanology. He says we will know for sure when the next earthquake occurs. The San Andreas Fault marks the boundary between the Pacific and North American tectonic plates. South of Parkfield, the fault is locked, meaning the plates are not moving against each other. To the north, however, the plates creep against each other at a constant rate of 1.4 inches per year. Parkfield sits in a transitional zone between these two areas. When this part of the fault becomes active, it typically produces a magnitude 6 earthquake. Because of its remote location, these earthquakes rarely pose a threat to human life or property. However, earthquakes on this fault can impact stresses on nearby faults, according to Malagnini. Researchers closely monitor Parkfield. They hope to predict the next earthquake. Finding reliable precursors could help scientists warn of impending earthquakes. These include rock strain and changes in subsurface permeability. This might save lives. Parkfield has a history of recurring quakes. It could be an ideal place to search for clues. These might help with more dangerous fault segments. However, this goal has proven elusive so far. Malagnini and his team measured seismic wave attenuation. It is how sound waves lose energy as they travel through the Earth's crust. Attenuation is connected to the permeability of the rock. Before an earthquake, stress causes cracks in the rock around the fault to open and close. The study found that, in the 6 weeks before the 2004 Parkfield earthquake, low-frequency waves lost energy while high-frequency waves gained it. Malagnini says stress between the Pacific and North American plates caused this change. As stress builds, long cracks form in the subsurface. They range from several hundred feet to 1 mile in length. These long cracks relieve some of the stress on the surrounding rocks, causing shorter cracks to close. This alteration in crack behavior explains the varying energy loss in different seismic waves. Currently, there are signs that Parkfield might be nearing the end of its quiet phase, Malanini noted. The timing is significant. Parkfield has skipped quakes before. However, these skipped events in the 22-year cycle happened when nearby quakes changed the regional stress. No such events have occurred this time. Another clue is that attenuation measurement variations have dropped since 2021. This is similar to what was observed in 2003 before the 2004 earthquake. However, there is no evidence of the bifurcation in attenuation measurements that preceded the 2004 earthquake. Malanini suspects the next quake could hit Parkfield this year. The epicenter may differ from 2004, leading to different measurements. Malanini is not trying to predict the next quake's timing. He hopes that, after it occurs, his team can find signals to watch for in the future. "I'll be waiting for the next earthquake," Malanini said, "and then we'll look back." NASA's new data and collaborative efforts. NASA's recent data confirms concerns about the San Andreas Fault. It is under significant stress. This new info highlights the need for greater vigilance and readiness for a big earthquake. NASA's tech gives precise data. It's vital for improving our earthquake risk models. Dr. Thomas Jordan, a renowned geologist, has highlighted the critical role of NASA's technologies in this context. He explains that using INSAR and other remote sensing tech allows for unprecedented accuracy in monitoring the fault. These tools let scientists see small movements and stress on the fault line. This is vital for assessing earthquake risk. Dr. Jordan stresses that we must invest in these technologies. They are vital for improving our understanding of seismic hazards. Dr. Kate Hutton has also addressed the implications of the increased fault activity and stress for public safety. She stresses that these signs show an urgent need to prioritize earthquake preparedness. It's not just a scientific issue. We must prepare communities for potential earthquakes. NASA's collaboration with the United States Geological Survey, USGS, plays a significant role in this research. The USGS has studied the San Andreas Fault for decades. It has valuable ground data, historical records, and seismological expertise. Researchers can combine NASA's satellites with the USGS's ground-based measurements. This will help scientists understand the fault's behavior better. Another key partner is the Southern California Seismic Network, SCSN. It is a consortium of over 60 institutions. The SCSN does research on earthquake processes. This includes developing computer models to simulate earthquakes and assess their impacts. NASA's data improves these models with real-time updates. It makes them more accurate. Caltech participates in San Andreas Fault research initiatives. Caltech scientists use NASA's data to study the fault. They want to learn its properties and how earthquakes form. The Earthquake Research Laboratory at Caltech is a hub. It analyzes seismic data and experiments to understand fault dynamics. NASA's work on the San Andreas Fault requires global cooperation. Scientists worldwide contribute by sharing data and methods. They share findings from similar fault systems. These global efforts help compare fault behaviors. They also improve earthquake prediction models. In response to NASA's findings, California's local and state governments have acted. They have taken steps to improve earthquake safety and preparedness. It is impossible to prevent earthquakes, but we are developing ways to reduce their impact. Thanks for watching, and we'll see you in the next one.